Hey folks, quick video about standard deviation, what it is, what it means, and how we use it when we're comparing two sets of data. So let's start off with a really simple little experiment, thought experiment. Imagine I've got two classes of children, class A and class B, and I want to compare them. I want to know, are the children in class B taller than those in class A? So I rush into each classroom, pick at random 8 students from each. Here are the 8 from class A, here are the 8 from class B. You could think, just by looking at those straight away, well, hang on, there's a difference there. The average of class A is about that, the average of class B is about that. They're obviously taller in class B. So we've reached a conclusion there. And that may not, in fact, be the case. Okay, so I've calculated the average for each. Here we go, class B are taller than class A. But what if I'd just accidentally picked all the short people from class A? What if I'd just chosen a random selection of students that wasn't truly representative? What if the class looked like that overall and I'd picked these guys up here? I might end up with my mean being quite different from the true mean of that class. So standard deviation is used to give you an idea of where the true mean of a population might actually lie. So without going out and measuring every single individual in the population, it gives you an idea of where that true mean might be. So to put this in some kind of context, we're going to look at a graph like this. Now ignore the numbers around the side. Don't panic about those. Just look at the bars to start off with. This could be used to show the heights of pupils in a class. And what this means is there are very few really short pupils. There are very few really tall pupils. Most pupils tend to be of that middling kind of range of heights, and in fact the most common height by far is the one bang in the middle, which is close to the mean average, which will be straight in the middle there. And you can obviously simplify this by not drawing the bars, but by drawing a curve instead. And those of you who are doing statistics, or maybe even psychology, you'll probably recognize this as our normal distribution curve. So with my class height example here, we got height on the x-axis, and this shows the frequency, i.e. the number of individuals that fit into that category of heights. So the mean for this will always be bang in the middle. And remember I said if you take a sample and you've got a mean, you hope that it's pretty close to the true mean, but you can't be certain. Because sometimes you'll end up with quite a lot of scatter around that mean value. So here are two populations with the same mean, but as you can see, in the red population, all the data is fairly closely clustered around the mean. There's not very many individuals at these extreme values. But in the black population, there's a much bigger scatter around it. Okay, and we're saying that although the means are the same, there's a lot more people who are very short and very tall in the black population. And that does have an influence on where the true mean might lie. So if you have two populations that have a relatively small scatter around the mean, and they look like this, then you can be reasonably sure the mean of class A, for example, and the mean of class B, they are actually genuinely different because they're so far apart that there's not very much overlap and there's not very much scatter in either population. But if you've got a graph that looks a bit like this, suddenly there's a lot more scatter in this population here. And the true mean, although we've calculated our mean to be here, the true mean of that population, well, it could be anywhere between there and there, say. And the true mean of this one could be anywhere between there and there. And there's an area of overlap. The true means of both populations could be found in this little area here. And they might actually be the same. And we have incorrectly concluded that those classes are different. So in order to assess how likely it is that we're making that kind of mistake, we calculate the actual standard deviation of data, which gives us an indication of how big the spread is around the mean. Okay, so that's what standard deviation is, a measure of the spread around the mean. And the equation for it looks like this, which is horrible. But actually, when you unpick what it means, it's really straightforward. So S, that's our standard deviation, is equal to the square root of sigma, the sum of x minus x bar squared divided by n minus 1. Okay, what does that mean? Well, x, that's every single sample. That's every single data point in your population you've sampled. And you're minusing from it x bar. That's the mean average. Okay, let's give a real-world example. So you've got these examples in your booklets. We're going to look at two giants of the daytime TV schedule. We've got Judge Judy versus Judge Rinder, and we've been measuring the heart rates in beats per minute of those watching, and it's obviously pretty exciting stuff because their heart rate's gone through the roof. But the question is, are Judge Judy viewers getting significantly more excited by the TV than Judge Rinder? Is there a difference in the heart rate? So if you have a look at these here, then obviously there might be a little bit of a difference you can see there, but we can't really unpick how different they are at this stage unless we do some calculations. So first thing we're going to do is we're going to calculate the standard deviation for the Judge Judy set of data. And to start that process off, you have to do a lot of annotating and scribbling figures down when you do this calculation, but none of the individual calculations are that hard. You've just got to be methodical. So here's our data as you have it in your booklet as well, between there and there. And the first thing you do is you add them all up, divide by 6 to give your mean value. So this is the mean beats per minute of somebody watching Judge Judy on the telly. You then do your x minus the mean, or as they call it over here, x minus x bar, okay? And you do that for every single data point. So x minus x bar. So I've taken 117 and I've subtracted 134.5 from it to get minus 17.5. Then I do the same for this one. I do 156 minus 134.5. I've got 21.5 and so on. And that's what I'm putting in this column here. Okay, so it's worth scribbling these on your result sheet as you go through. Some of these are negative numbers, some of these are positive numbers. If I were just to add these all up, well, I'd probably get 0. It wouldn't tell me very much at all because the negative numbers would cancel out the positive ones. So a much better way to get an idea of the scale of the difference is to square it all so that everything's positive. And that's what we've done here. X minus the mean squared, that's x minus x bar squared. So I'm now looking at this bit here. So by squaring all of these numbers, they all become positive and then I can add them up. That's the sigma bit there. So adding all of these numbers up gives me 1013.5. Okay, that's my sigma x minus x bar squared. And now I'm going to divide that by n minus 1. Now n is the number of samples I took when I was collecting my data, which is 6 in this case. And we're doing n minus 1. You may occasionally see the equation without that minus 1 there, particularly if you're doing maths with stats. In biology, we always do n minus 1, and that is because you do n minus 1 when the data you're looking at is merely a sample of the population. So we haven't gone out and measured the pulse rate of absolutely everybody watching Judge Judy. That would be impractical. We've taken a subset of them. That's why when you calculate the standard deviation here, you do n minus 1. Okay, so in biology, there's always going to be that minus 1, which means n minus 1, that's 5. I'm going to be taking this and dividing it by 5. To get 202.7, and then you can see the whole thing is covered by a square root symbol. So I square root that, and I get 14.24. Okay, that's my standard deviation. I can do the same thing with Judge Rinder, and you get a slightly larger value here. The standard deviation in this instance is 28.27, so slightly larger, which is indicating that there's actually a bit more spread about the mean, and the mean value itself is different as well. Notice 130.7. versus 134.5. Okay, so what we've got there is a comparison of the standard deviations. Let's go back to our PowerPoint and have a look at what that actually means. Now I've got these standard deviation values for both populations. How can we use it? Well, remember I said that we're going to use our standard deviation to figure out where the true mean might lie. Remember, we've got a population of people watching Judge Judy and Judge Rinder, and I've taken a sample of them, but the true population looks a little bit like this. Now, because these kind of populations in biology always follow this normal distribution, it means we know one or two things about the way the data is distributed around the mean. This normal distribution follows a predictable pattern, and we know that about 68% of the data points, or in this case the individuals watching the TV, will have a heart rate that's within 1 standard deviation of the mean. So 68% of the population will have a heart rate that's within 1 standard deviation of the mean. That's the grey area of this graph. 95% of the population will have a heart rate that's within 2 standard deviations of the mean. So now, because I've calculated the standard deviation for both Judge Judy and Judge Rinder, I know with a pretty high degree of certainty where 95% of the populations watching those two TV shows are going to be. And that means I know with a really high degree of certainty that the mean value, the true mean, is going to lie somewhere between those two values. Okay, so even though I've only taken a sample, by working out the standard deviation, I know that my true mean is going to lie somewhere between these two values. And I can be pretty confident of that, because we know that 95% of the data lies between those two regions. I would be pretty unlucky in taking my sample to have picked people who are so out of the ordinary that actually I've skewed my average beyond where it truly lies, beyond that proper 95% range. Okay, so looking at Judge Rinder and Judge Judy, what we're going to do is we're going to produce a graph that looks a bit like this, and here's how you do it. Okay, you take your means for each of them. So those are the two means. There's a little bit of difference there. You put your standard deviation underneath, and then you work out your mean plus 2 standard deviations. Okay, so I've added 14.24 twice onto 134.5, and you get 162.97 ish. And then on this one, I've done the mean minus 2 standard deviations. So if you plot those values there and have a look at how the bars interact, you'll end up with something that looks a little bit like this. So this is showing plus or minus 2 standard deviations. And remember, 95% of the data, 95% of the population are going to exist within this range. So even if my average here is not very good, if my average is not very close to the true average, 95% of the population will be found within this range. So actually, that means that I can be pretty sure the true mean is well within this range somewhere. Now let's have a look at these two graphs here. You can quite clearly see that although the means that I've calculated are different, there's a massive overlap between the plus or minus 2 standard deviation bars. That means it's likely that this variation that I've observed here is actually just due to chance. It's quite possible that the true means for these two TV programs are actually the same, that the people who are watching them have the same pulse rate. We cannot conclude that there is a significant difference between them because the standard deviations overlap. Sometimes you get plus or minus 2 standard deviations, sometimes it's plus or minus 1. It's doing the same thing. It's looking at how much overlap there is and how likely it is that those two mean averages are actually different. And the phrase you need to get used to using is that the standard deviation bars overlap, therefore it is unlikely that the means are truly different. Or, in a more exciting set of data, you might say the standard deviation bars do not overlap. It is very likely that the means are truly different. Okay, so remember this, when you've got a set of data like this, you calculate a mean, 68% of the population will be within 1 standard deviation of the mean. Okay, and that's standard deviation. I hope that was useful. Have a go at the examples in your booklet.